In 28.2, we talk about the introduction to magnets. Magnets can come in many different forms, and their electric fields can be shown in different ways. It is important to remember that magnetic fields travel from north to south poles, also known as positive to negative. No matter what orientation, it always travels from north to south, as you can see from the different illustrations. There are two types of magnets, an electromagnet and a permanent magnet. Electromagnets are produced by an electric current where the current runs through a wire. Permanent magnets are a magnet that retains its magnetic properties in the absence of an inducing field or current.
In chapter 28.3, we discuss magnetic fields. A magnetic field is measured in Tesla and needs three components: a force, a charged particle, and that charged particle has to be moving. When we solve for the force, we discover that it's a cross product, meaning that it's the sine of the angle. The component we want to consider for the charged moving particle is the component perpendicular to the magnetic field. This may mean that the charged particle is on an angle.
In section 28.4, we talk about cross fields. The best way to describe a cross field is through illustrating an old tube TV. Thomson examined the effect of a magnetic and electric field on an electron as it passed through a cathode ray tube. While doing this experiment, he found that he was able to control the electron as it passed through this arrangement of fields. By doing this, he was able to take the electron shot from the power source and was able to direct it onto a screen at any angle that he wanted. He was able to use the magnetic and electric field lines shown to direct the particle to the designated spot that he wanted. Thomson's new discovery was used in the production of many TVs that were sold during this time. Although Thomson's technology has been outdated, it is still used in many experiments today.
In 28.6, we see how a charged particle moves through a magnetic field in a circular manner. So using Fc, we can set that equal to Fb. Knowing that mv squared over r Fc equals qvb Fb, we can solve for velocity, finding that qbr over m is equal to that velocity. In 28.8, we see when a wire has a current, it produces a magnetic field. In our depiction, the magnetic field is coming out towards us. The force created by the magnetic field pushes all the electrons towards the bottom of the wire. This will cause the wire to bend until it reaches an equilibrium point. Knowing that Fb equals Qv cross B, and knowing that Q equals I cross L over V, we can substitute Q into the formula for Fb, and we get the force on the wire equals Lbi.
In this section, 28.9, we discuss the torque on a current carried through a wire within a loop. As you can see in the picture, that the current always travels around the wire in opposite directions. This causes the charged particles to move in opposite directions. As you can see on the right, the charged particle is moving in the north direction. If you put your fingers lined with the field lines, pointing to the right side of the screen, and your thumb facing upwards, you see that the palm of your hand is facing into the screen where the force is equal to. On the flip side, you see that the charged particle is moving in the south direction, and the field lines are moving in the same direction, so now you flip your palm, and your palm is pointing out of the screen. This causes the wire to have forces in opposite directions. As a result of the wire having forces in opposite directions, it is able to move in a circular motion. The force of the wire results the wire to spin. This realization is used today in many occasions where electric motors are involved. Whether it is as simple as a drill or as complex as a car, electric motors have enough torque to power themselves and to fulfill themselves as efficient motors.